with the visionary leadership of Professor K. Madhumurthy Garu, Chairman, AP State Council of Higher Education. We are parallelly uh, taking up both quantum computing, quantum technologies, as well as artificial intelligence, as both are cutting-edge technologies. And in this series, to adjust the workload, a series of quantum technology programs are going on every day. And on Saturdays, we have exclusively conducting the webinars on artificial intelligence. And in this series, this is the webinar series number 13. The title of this today's very important topic is the quantum computing towards advantage. The quantum computing and AI, artificial intelligence towards advantage. Today's here is a very important, very young and dynamic leader in the quantum computing and AI from IBM. I would like to introduce a brief biodata about today's resource person, Dr. Dhinakaran Vinayagamurthy. He is the currently manager of the Qiskit team in India at IBM Quantum, Bangalore. He is also an adjunct professor in the Department of DSAI at IIT Madras. His research in quantum computing, cryptography, and blockchain has resulted in about 20 peer-reviewed publications. And of these 20 publications, the beauty of this publication, beauty of his research is he has got 16 patents with around 1400 citations by today. He has received the Best Paper Finalist Award at the ACM CCS IBM Internal Awards, like outstanding technical accomplishments, technical collaboration, achievement, and one IBM ISA Growth Award, respectively, for his contribution towards research and innovation. His significant contributions include to open source and IBM India market growth, respectively. This is really very enterprising. He has been a lead coordinator or instructor in NPTEL courses. And as you know, I once again request all the participants, all the faculty members to encourage all our students to register this NPTEL course, which is on quantum computing and algorithms, which is going to commence from 19th of January. I think we have already record number of students enrolled for this NPTEL course to be conducted from 19th January 2026. I request all the faculty members to share this to your all students. Even the faculty members also can join this course. And as per our request, that is, our chairmen are very keen in promoting both this quantum computing, artificial intelligence, and semiconductor, fab, etc. So, upon his special request, the NPTEL has agreed to offer this course for a very nominal amount. Actually, for all India categories, it is 1000 rupees, whereas for AP students, if he want the certificate, the price will be only 500 rupees. And that too, for other communities like SCSTs, it will be reimbursed again if they pass. And the enrollment is very free. The enrollment is free. So everybody can enroll freely and attend the courses. And if they are serious, they can prepare and they can get the certificate. Not only that, our honorable chairman is coming up with a very innovative idea that the WISER program that is already going on and this NPTEL, and immediately after this course, we are also actually offering internship program in the long-term course. So altogether, they will also offer the internship credits also. And about the Dhinakaran, he has been a lead contributor for this NPTEL course also, and he is also going to take some sessions. So I request all the faculty as well as students, please kindly share the YouTube live link to your students as well, because it is also live streaming. The ACM Winter Schools and Faculty Development Programs, he is very actively participating across India on quantum computing especially. He had also served as the first Quantum Innovation Center lead for India at IBM Quantum, where he managed the research and business partnerships in this region. So it is very great thing, such an young age, he is contributing to the nation as a whole on this quantum research. He manages the research and business partnerships in this region. And as the technical assistant to the director of the IBM India Lab and CTO, IBM India South Asia, he holds a PhD in computer science, quantum information from University of Waterloo. That is very important university. Sir, I would like to convey one thing. Most of our syllabus for major and minor we have taken from this Waterloo University, specifically on this quantum technologies. A master's in computer science from the University of Toronto and a bachelor in computer science and engineering from the College of Engineering, Guindy, that is Tamil Nadu. I welcome you, sir. Now the floor is open for you. You can um, present your session. The session will be up to 12:30. Meanwhile, you can also interact with our participants. Thank you, sir. Thank you. And on behalf of Akshay, I profusely thank you for sparing your valuable time. Although you are very busy today also, I profusely thank you and welcome you, sir.
Okay. Yeah, thank you, Dr. Anil, for the very kind introduction, and like overall, thank the Chief Minister Chandrababu Naidu Garu and the visionary leadership. I mean, usually, as a technical person, we don't, uh, you know, like we don't really see uh, the visionary leadership of political leaders, but then the amount of progress that we have seen firsthand in the state and in the country in quantum computing. I mean, we should certainly, after 10 years, when we look back, some of the decision and the visionary leadership of the leaders in the state of Andhra Pradesh would have played a very, very significant role for the broader country. And I'm happy and sort of proud to be part of all these initiatives. So actually, thank you, sir, for organizing all these activities, including the webinar series and the courses. Like there are very strong foundations set, and we are really, really looking forward to seeing the fruits of all the things that we are doing starting last year uh, and going forward. So yeah, thanks a lot to all your team for doing it. Today, let me just share my screen. Uh, share my presentation. Okay. Can you see my screen?
It is visible.
Okay, good. Okay. Good morning and welcome everyone to today's talk around quantum computing and its relevance to AI. And like, since it's an AI series, uh, I thought I will give an overview of what the technology is about, and like I and our colleagues are preparing the broader courses around quantum computing. But today, since many of you would have been relatively new to this area, I thought I will take some time to give an overview of what quantum computing is about, what where we are in right now, and then the next section I will go towards discussing the different applications of quantum computing and its relevance to the broader field of and its synergy actually like to with the broader field of artificial intelligence. This is more about how quantum is influencing the areas where AI is trying to influence, and then sort of looking in the other direction, I will also give a perspective about how we leverage the current classical artificial intelligence methods to improve our, let's say, building and the using of quantum computers. Okay. And then finally, as you all are trying to learn and teach quantum computing and AI, I just have a set of things I wanted to bring as resources that you should use, and some sort of suggestions and guidelines that we can use. Looking back from our experience of doing it over the last 4 or 5 years across India, I thought it'll be a good sort of place to summarize some of those things. Okay, all right. Okay, so what is quantum computing? And it has generated a ton of interest in India and across the world. I mean, India, we have the National Quantum Mission that was sort of envisioned in 2020, and then it sort of really started 2 years ago. And there has been a very significant progress to that. And then AP has had it came in, maybe relatively speaking, a few months or a year late, but then has really, really pulled along the entire nation in terms of the efforts in quantum computing. And many other states have significantly followed up. It's sort of just the preview, and I think almost every major state in India has sort of set a vision in quantum computing, right? So, what is really the interest, right? Because we also have the Quantum Valley Tech Park coming up in Amaravati, uh, like this year, right? We are just few months away, right? So, given that like all this very interesting thing is happening, what is all the interest about, right? So, to give an overview, to give a high level context, I just wanted to go back a century or so, right? Like how computing has really progressed. In the 1800s, we have had like very simple. If we look back now, it's maybe it was complex at that point of time. We have produced computers, or more simply calculators, that performed individual operations mechanically. And then sort of 50, 70 years ago, there has been a major transition towards building computers from electronics, and that sort of revolutionized, going from vacuum tubes, transistors, IC, microprocessors, to all the broader CPU, GPU, and specialized AI compute that we have had in the recent past. Uh, so that sort of, if you look at, let's say, the power of operations per second, it improved from, let's say, one computation per second to sort of an order of magnitude of improvement almost every decade. And we can do about, like, this is one sample of one of the supercomputers in the last 5 years. It can do about 200 quadrillion calculations per second. Like, what is quadrillion? Quadrillion is about 10 to the 15. We're talking about a single unified computer that can do about 10 to the 15 or much more. This is even like slightly outdated from 5 years ago. So we can probably do maybe close to, I don't know, 10 to the 18, or maybe even 10 to the 20 calculations per second, if you think about specialized calculations. And you can store about petabytes of data, again 10 to the 15 or so. We have tens of thousands of GPUs. So this begs the question of, okay, what is that we can even not do with this kind of a computer? Like, what is the interest in developing sort of new kinds of computers? Are there problems that are intractable, or that is something that cannot be solved in if we just continue building these more powerful computers? The simple, very non-detailed answer to the question is to give a preview of the power of a qubit. Let's say qubit is a single unit of information of a quantum computer. Just to compare with what's possible and how it compares with the best supercomputers we have today. Okay, so if we have a 30 qubit system, so like there are some assumptions that I'm making, which is that all the 30 should be perfect, without any noise, and sort of all to all connected and so on. That's a technical detail. But then if you have a perfect 30 qubit system that can exist in a quantum computer, that's already sort of a power of what a modern laptop uh, can perform, right? And then it sort of quickly escalates, quickly scales up. If we have a 48 perfect qubit system, right? this already can store information that's as much as that can represent information. To represent a fully 48 qubit perfect system, it takes the power of a supercomputer that I talked about before. I mean, the numbers in the previous slide look mind-boggling, right? Like 10 quadrillion petabytes. I mean, terms that we barely use on a day-to-day basis for sure. But like even the most advanced scientific calculations try hard to push to the limits of this. But then all these like magical numbers, you sort of require even to represent perfectly a 48 qubit system, and then it sort of even quickly sort of ramps up. If you want to perfectly represent a 60 qubit system, then it needs the power of almost all the classical computers that are on earth too. Okay, so this sort of says that if we have perfect quantum computers, and this shows sort of gives a glimpse of the promise of what it can do compared to even the most powerful computers that we have today without leveraging quantum principles. I mean, this is just one illustration, and hence this is actually not an extension of the current set of classical computing architectures. I would say this is more of a paradigm shift in coming up with a new type of computers, and the promise is actually very high, right? And given that you have teachers from and listeners from across all departments, if you are a, let's say, a computer scientist, if you have seen complexity theory, this is roughly trying to categorize the hardness of problems that can be solved theoretically speaking. Let's say we think about all the easy problems that we can solve in using the current set of computers that we have today as the class P, the polynomial class of problems, the things that we can solve in polynomial time. And there are like many more hard problems that exist in NP or even beyond, right? That cannot be solved efficiently by the computers that we have today and that we will ever have, right? Classically. And what quantum computers give the promise is it sort of significantly extends the class of problems that we can solve, that we will ever expect to solve efficiently on a classical computer. Okay, so even theoretically, if we look at it, there is a lot of promise that's involved, and all the efforts in the last decade or more has been in realizing the theoretical power that has been demonstrated in practice. Okay, so like just a very quick differentiation of like where quantum computers are different. uh, it's actually different from the most basic principles of building a computer, right? Like in the computers that we have today, including the computers that I'm using to give a talk and you are using to listen to what you're doing, and the smartphones and anything that we use today, the most basic unit of information is called bit, where the most basic unit of information is either 0 or 1 at any point of time. And then we have different operations defined to perform some computations on that at the most primitive level, and these get abstracted at various levels for us to do all the advanced computations that we want to do. Quantum computers differ from those most basic unit of information itself. So the most basic unit of information is called a qubit, where you can have some, let's say naively speaking, some probabilistic combination of 0 and 1 at the same time in a single unit of information. Okay, and this, when we have multiple sort of these things, we can also have some advanced operations that we can perform over this particular combination of probabilistic combination of 0 and 1. Okay, uh, so there are some of these more fundamental principles called superposition, which is what I talked about in the previous slide about a single unit of information being in a complex linear combination of two states. And then across these two units of information, you can create this so-called entanglement, or naively speaking, some kind of a correlation between those multiple units of information, where in doing some computation on one actually influences the other without even touching the other. Okay, and there are also ways where it lets you do interference where you can either sort of combine the useful signals in a positive way to amplify that, or you can also have this so-called destructive interference where which we can leverage to sort of reduce the, let's say, unnecessary parts of the information that we have. Okay, and none of these are sort of magical. We are not creating something, these principles out of thin air. This is in fact how nature has behaved forever, right? It's just that right now we are leveraging them to build a general purpose computer out of these basic principles. Okay, and in fact, in the 1980s itself, Richard Feynman, who was one of the best scientists, quantum scientists available in those decades, he said that anyway, nature is not classical. Nature is anyway quantum mechanical. So, if at all we are trying to process information, why don't we just build a computer that is leveraged out of these basic principles? And leveraging quantum mechanics is not new for our world. In fact, like there are many things that we use today at a very broad scale and that has generated like sort of trillions of dollars of commercial impact have been fundamentally leveraging quantum mechanical principles, like starting from the lasers that we use, or the MRI scans that we use, or the solar cells that like exist across the country right now, the LEDs and the different polymers. I mean, these are things that we sort of see on a regular basis, if not a day-to-day basis. Some of these, right? These are ever present, and these have strongly leveraged the quantum mechanical principles. And what we are currently pursuing towards is to build a general purpose computer out of these like quantum mechanical principles, because these are like specialized things that we did leveraging that. And the current goal is to build a useful general purpose quantum computer that's leveraging the power of the quantum mechanics. Okay, I mean, and this goes in sort of two parts. First part is actually building the computer in itself that outperforms the classical computers that we have today. Building the hardware, building sort of the middleware components, like let's say the operating system and any of the system software that and the middleware that sort of helps us leverage the power of hardware. And the second part is coming up with new algorithms, applications for the hardware that we have built. I'll take just some 10 minutes to give an overview of the current state of the hardware before I go into the applications and then AI parts of it. So, I mean, like, how does sort of the full stack for quantum computing look like? Of course, we have the sort of the quantum chip, the processor, and the core hardware components, the electronics that control the processor, and so on. And we will have this equivalence of the modern operating system that sort of manages the resources of the underlying quantum hardware. And also, anyway, like we will have a quantum hardware that will be working alongside the current computing hardware available, right? So we'll have a resource management layer that sort of works across all the quantum and the classical resources we have. And there are one more levels of abstraction for each of the things that we do, going up to the top where we have like new algorithms and different applications, which is sort of the highest layer of abstraction with which we use any system, right? So since it's a very new type of a computer, we'll have to rebuild and reimagine some of the intermediate layers to leverage the best out of the underlying hardware. Yeah, maybe this is something that I will do at a later point as well. Like starting with the hardware, you have like different components for different functionalities at different. And like I mentioned before, something I want to really emphasize is that we're not saying that, okay, like this particular quantum hardware that comes up like sort of replaces every computer that we have today. There are many kind of sort of simple computations that we do that we will still continue to leverage the current computers we have today. but there are some, let's say, some of the complex computations and many of the advanced scientific computing experiments, or many of those which cannot be performed in an efficient manner, how much ever supercomputers we have. And those are the kind of problem statements where we'll explore the possibility of using quantum computers. So overall, if you see an end-to-end computation, even let's say 10 years later, if not more, we will see a sort of a hybrid quantum classical architecture, and we'll have let's say a quantum centric supercomputing center that's built, which we will leverage uh, the best of all the let's say quantum and classical resources available. This is how we anticipate any industry scale application to uh, sort of use in the next decade at least. And yeah, okay, this is one of the things we already started demonstrating. This is not something we're just saying in theory. For example, like in Japan, Fugaku is one of the most modern supercomputers available today. And last year we had a quantum computer that's placed and connected with the Fugaku supercomputer, and demonstrated many like state of art research results, cutting edge research results, some of which I will cover in the later things. And we are hoping to setting up something very similar in the Amaravati Quantum Valley as well. This is just something I will leave it to you as a pointer, that if you want to go into more details, like every year we release a roadmap of what we anticipate to build in the next 5 years. Okay, and we had been doing that from 2016. For the last 10 years, we had been, publishing a 5 year looking ahead roadmap. And this is something you can search online as well. And this sort of gives a summary of, how we have evolved from 2016, from let's say a 1 qubit, 5 qubit system to where we are today, and then how we anticipate, uh, how we expect to build upon our research to develop some of that most advanced quantum computers and sort of large commercially useful quantum computers towards the end of this decade, right, for the next 5 years. And I'll just highlight two trends here. So one is, you can certainly rapidly see the rapid progress of the scale of hardware and each of the layers evolving. And as the hardware scales, there are many layers of abstraction built to make it easy and easier for the end users and for the computer scientists and for the domain experts and application developers to make the best use of the more advanced hardware. Because as it scales, it's you need many sort of intermediate layers for which we need a significant quantum expertise. But then once we build those layers, it's easy for those who are domain experts in their respective domain to leverage that. So if you are a teacher teaching quantum computing, or if you're a researcher or a student, or even an industry member working on this, you can come from your point of expertise and then leverage the best of the computing tools available. And if you're a researcher in quantum computing in itself, you can go underneath some of these layers of abstraction to either leverage some of these low level tools better, or you can even contribute to some of these, improving some of these low level tools, because year on year there has been like significant improvement up and coming always. Okay. All right. So, any quick questions before I go into the next section? I'm not able to see the screen. So. Okay, I don't see any questions in the chat, so I'm assuming I can go ahead. Okay, maybe if there is something, one of you can unmute and ask me. All right. So the next section, I'll talk about, okay, the different applications of quantum computing and like how I see connecting with AI. Okay. Just a preview of this, and then I'll give pointers later. First of all, okay, what are the different areas where we expect quantum computers to be leveraged the most? The first area is something called as Hamiltonian simulation. You can think of it as simulating nature processes. You know, like I mentioned before, let's say the chemical process and the biological process are inherently quantum mechanical. Until now, we had been sort of simplifying it and abstracting out to the current computers we have today, and then trying to process them. Okay, whenever we try to simulate something, and since quantum computers inherently provide a way to sort of encode such information and process on top of that, that is one of the most promising uses of quantum computing. And second is sort of the large class of optimization problems. I talked about, you know, uh, qubit being in a probabilistic state and then being able to represent, I mean, sort of multiple qubits being able to represent exponentially more information than what we can do in a classical world. So there are some of these optimization algorithms that try to leverage these uh, properties of a quantum computer to solve with much more accuracy, or hopefully solve with more efficiency in terms of time, the various constrained optimization problems that has been hard to solve in any of the modern computers we have today. And very similar lines, very similar principles, like I said, for optimization, we can. There has been like strong research that also tries to improve uh, the modern machine learning architectures, or try to come up with new machine learning architectures that leverage the exponential state space that quantum computers like let us encode data and represent data and process data. Okay, I'll give a preview of some of these. And then the fourth sort of class of applications is also in this processing differential equations that have that in turn have applications in many of the strategic sectors, uh, including let's say defense and other areas, or many of the mechanical areas, where quantum computers provide sort of new ways to solve some of the complex type of differential equations that have been proving exponent like sort of very like hard to solve on any of the supercomputers that we have today. So that's the fourth class of applications. And then if you think about it, these four problem statements are not unique to a specific industry. I mean, you have, as we explored more and more, what we realized is some of these problem statements have found applications in a broad set of domains, in, I mean, the broad set of sectors in industry, ranging from aerospace, automotive, chemicals, electronics, or energy, financial services, healthcare, everything. Like there has been, uh, in each of these domains, there are some like optimization problem or a machine learning problem. And in most of these domains, there are like differential equation solving or Hamiltonian simulations that exist. And as we, build more new and newer algorithms, uh, since we have a sort of a large network of collaborators from industries and other many other government organizations, we see that each technique that we find in, let's say, one of these areas have one of these sort of technical problem areas have found applications in different broad sectors in industry. And some of these that I have listed here, in fact, many of these I've listed here, are concrete problem statements that we have explored with the leaders in their respective industries and try to push the state of art in what can be done leveraging quantum computers. And the reason I went for this broader set of applications rather than just focusing on, let's say, just the specific quantum machine learning algorithms is that in the last 10 years, machine learning has made significant progress in a very broad and general context that many of the modern machine learning tools have been used in across all these industries and for many of the problem statements that we have listed here. So since machine learning has had a very broad set of applications, I thought it's also useful for you in the audience to understand, okay, the sort of a type of problem statements that quantum can also solve, so that when you look at machine learning application for any of these industries, you try to understand, okay, like what machine learning can solve and where is the limits at this point, and where quantum machine learning, where quantum computing in general can help in that, and then try to understand, okay, like how they can be used well together, or you can even research on improving uh, the state of art by leveraging those, because each of the quantum techniques and the classical machine learning will have its own pros and cons. So can we have a higher level algorithm that can better leverage the advantages of each of these in a more significant manner is something we can explore across these domains. So since machine learning has been cross-cutting, I thought it's useful for the audience to also explore this. And maybe one specific, given that it's supposed to also be a technical talk, I thought I will also, go into, a very high level overview of one of the modern quantum algorithms that has found applications across many of these problem statements that I have mentioned before. This particular problem statement was first demonstrated for this chemistry simulation problems, especially let's say simulating this Fe4S4 molecule. And that particular method, if when leveraging the classical exact methods, it required 63 petabytes of memory, and it needed like a lot of time to solve it. And even a classical approximate method required about 8 hours to solve that particular simulation problem. But leveraging the quantum classical hybrid algorithm and using actually uh, the supercomputer that I mentioned in Japan, the facility that we had set up, right? The quantum classical algorithm run on that required a 12-minute quantum processing time and a 1.5 hours of supercomputing time to get very close to this classical state of art method compared to taking 8 hours on a classical method. So this particular problem statement was actually, this particular technique that was introduced, algorithm that was introduced, was initially for like chemistry simulation, but then later we have sort of extended research to solve something very interesting on optimization and machine learning problems as well. So I thought I will take some 5 minutes to give a very quick overview of this, at least as a starting point, and then you can maybe read more about it later and teach about it. So yes, this particular technique, this is sort of the how the scale of molecular simulation has been happening using quantum computers, but this particular algorithm has rapidly improved the state of art and how someone can leverage quantum computers for new problem statements. And one of the main reasons I try to connect across these different applications of quantum computing to specifically, let's say, learning and like machine learning and type problem statements is that many of the chemistry problem statements that people try to solve, industry tries to solve, you can write it as the problem of finding the ground state of a particular quantum system. This is what people say, like finding the lowest energy state of a particular quantum system is one of the core problems that we try to solve using quantum computers. And we mathematically look at it, the same thing, it's equivalent to saying that, okay, if we have a quantum system represented as a matrix, usually a extremely large matrix that even the most powerful supercomputers find it hard to process, finding the ground state is equivalent to saying that we find the eigenvector corresponding to the minimum eigenvalue of this matrix. Okay, so typically what quantum computers try to solve for, let's say, some of these chemistry, biology, nature simulation problems, the underlying mathematics is essentially finding the eigenvector corresponding to the minimum eigenvalue for a matrix. Okay, and I mean, if you have, since you have studied like machine learning for a period of time, you can already sort of appreciate that this, like being able to do this, provides a lot of power for many of the machine learning problem statements. Okay, so this is sort of one of the fundamental connections I see between how someone can leverage a quantum computer to solve some of the machine learning problems. Of course, there are different levels of abstraction, and one like sort of this particular method that I talked about, where we leverage uh, like that showed the result that I mentioned in this particular slide, like that simulates Fe4S4, has a specific way of finding the minimum energy state, or finding the lowest eigenvector corresponding to the lowest eigenvalue. Maybe this picture doesn't actually quantify the hardness of the problem statement, but let's say, you know, many of the popular scientific computing algorithms, which sort of use the most powerful supercomputers that we have today, try to find a ground state support in a very large sort of among the full Hilbert space. Okay, and one thing that we can potentially try to do is to identify a subspace that is easier for us to process, and within that we can find the ground state. But then the hardness now comes down to identifying the right subspace. So if at all we are lucky, and then if we just randomly sample from it, and if we just happen to identify the right subspace, then okay, fine, it's easy to solve within that subspace and identify the ground state. But then if we do not find the right subspace, then our ground state is not accurate. So essentially finding the right subspace is as hard as solving the higher level problem statement that I mentioned, which is finding the ground state, which is the minimum eigenvector corresponding to the minimum eigenvalue. And what we have realized in the recent past is that quantum computers are extremely good in sampling from extremely large spaces. Okay, so what we have done is use the quantum computer to, I mean, we sort of guide the quantum computer on, okay, like what kind of subspaces to sample, and then use the quantum computer to sort of sample from the largest space. And then once we find the subspace, we give it to one of the supercomputers, and then just do the traditional routine of finding the minimum eigenvector corresponding to the minimum eigenvalue for that particular subspace. It's also so called diagonalization, right? We do that, but we have realized that sampling using a quantum computer has been like extremely powerful, uh, and we couldn't replicate. There are many, I mean, it looks like a simple enough problem statement, so people have tried, like many researchers, collaborators have tried running this on a classical computer, and it has never given that accuracy close to what a quantum computer could give in terms of quality sampling from a subspace, a quantity sampling of a subspace from the largest space. So this is one of the things that we leverage, and of course there is an end-to-end method on, okay, like how do we sort of, if we want to solve a particular either a simulation problem statement or an optimization or even a machine learning problem statement, how do we represent the problem statement in terms of I mean, there's a term called ansatz, but how do we encode the problem statement to a computer? That's the first step. And then we leverage the quantum computer to sort of sample subsample from the larger space. and then we will leverage the classical computers to find the lowest energy, and that solves a larger problem, right? So it's sort of an iterative algorithm that we run, where we can also adapt the subspace, and we do. And this particular thing, as I mentioned, if it was a chemistry simulation problem, then it's a molecule that we sort of prepare the digital representation of it that we can encode in a quantum computer. And then we do the sampling on a quantum computer. And then once we get the samples, we leverage a lot of, like the modern supercomputers, the GPUs and the CPUs, to post process the result and then find the minimum eigenvalue. And like I said, that had, or maybe that's the one slide I was missing. So there are sort of many different very interesting pushing the state of art algorithms in many domains that leverage that. And then uh, very recently, we have also realized that there are some very interesting quantum machine learning algorithms that can be leveraged based on a variant of the algorithm that I mentioned in the previous slide. Okay, so essentially, like the thing that I want to say is that there are many of these fundamental advantages of using quantum computers, and those are the places that those are all the algorithms and the techniques that we use to advance the state of art in machine learning as well. Okay, and that's actually one of the core places where we can leverage quantum computers to advance machine learning. Okay, and yes, overall, there are many of these sort of applications across industries where quantum computers had been useful. Let's say, like in leveraging better batteries for EVs and electronics and storage. This is collaboration with Mercedes-Benz and Mitsubishi Chemicals and so on. And there was collaboration with Boeing to design like sort of better materials to be used in our airplanes, for our airplanes to be like more efficient and more cost effective and so on. And there was also research with Moderna. It's a very, it's one of the producers of the mRNA vaccine. So to develop new classes of antibiotics, and then there was also collaboration with Bosch about designing optimal superconductors for MRIs and so on. And yeah, maybe for purpose of time, I'll just go to this slide. You know, I talked about solving better. I try to connect this minimum ground state of quantum system problem to the eigenvector solving problem for a very large matrix, where quantum computers will be powerful for learning applications. There is one other fundamental principle, or one other fundamental algorithm that has been very powerful for quantum computers, that had really ramped up the interest for quantum computers in the 1990s, where that techniques from that also potentially could be used to design new quantum machine learning algorithms, right? So this specifically, I'm talking about Shor's algorithm that was proposed for solving prime factorization at a large scale. So prime factorization is used in the so-called RSA algorithm that forms the foundation of the security of internet that we use today. And Shor mentioned in the 1990s, I mean, where 1994, where we're talking about, I don't think internet even existed at this level, and there was not even security. But even back then, he talked about, I mean, he proposed a quantum algorithm that can solve a problem that became a foundation for security of quantum internet exponentially faster than any classical computer could do. Okay, and The underlying core mathematical problem is called the hidden subgroup problem, and that sort of breaks RSA and discrete log and other sort of cryptographically relevant problems. And there is this quantum technique called quantum Fourier transform that has been very significantly leveraged in in fact, one of the primary reasons for the speed up of uh, Shor's algorithm. And derivations of that can also be used to perform, like to identify and to come up with new quantum machine learning uh, algorithms. Okay, because at the end of the day, this is solving a particular mathematical problem faster, and there are different ways you can leverage this. So one of the research was about, okay, if at all we have a data set that is complex, that you know that embeds the hardness of this particular kind of a mathematical problem, then it has been shown that only quantum based machine learning algorithms can uh, perform an efficient classification of such a data set, and none of the classical algorithms were able to differentiate between provide sufficient accuracy, any reasonable accuracy for classification task on those. And I don't know, like there could be further research to better use some of these foundational quantum things to develop better quantum algorithms. And overall, we have also had research in where quantum based learning and optimization and data processing algorithms can be used across different industries. So starting with, let's say, improving anomaly detection, right? So we have a large data set, we have to find, let's say, a needle in a haystack type, solve needle in a haystack type problems where we know that very negligible quantities in the data set are anomalies and we want to detect them. And there has been some interesting collaborations with CERN or and then in fraud detection with some of the financial collaborators about improving anomaly detection using quantum algorithms. And then if when we have a large, the second thing is, I think this is a collaboration with Cleveland Clinic Foundation, which where we have large data sets of patient records, and then how do we leverage quantum based algorithms to further improve patient outcomes. Outcomes for certain treatments for specific patients, understanding by better understanding their the patient records. And there has been like interesting time series based prediction algorithms, and I think Credit Mutual is one of the banks where we try to collaborate and learn improve some of the risk management techniques through some of these time series algorithms. And then when collaborating with Hyundai, there has been large scale sort of logistics networks and vehicle routing algorithms that we could leverage quantum computers to solve some of them. So just to give a preview of, uh, given that you had been studying AI, you probably will see AI applications across all these problem statements. So it will be useful to understand, okay, like where AI can do, what are the limits of it, and then where quantum and AI can work together in some of these things, because these are the places where quantum computers had been leveraged to improve the state of art in some specific aspect of these real world industry problem statements. I also had some slides on the specific HSPC work on how quantum machine learning was used to, or specifically a multi-kernel learning algorithm was proposed on top of, I think, the quantum SVMs, quantum support vector machines, to improve the fraud detection algorithm that they had used. And yeah, this is the patient outcomes talk where I talked about quantum neural networks being used to better leverage the data. And then this is also, for scientific experiments, you would have heard about, gravity experiments, like Large Hadron Collider experiments, which generates some, I think, petabytes of data. And usually researchers try to uh, find some new kind of particles in those data. This is also one kind of anomaly detection algorithm. And quantum-based learning methods had reached like a similar level of accuracy in a very short period of time compared to a classical method that had been developed for many years and in fact specific to this problem statement. A general quantum learning algorithm could reach a level of accuracy that in a like it would catch up with the classical state of art very fast. Okay, so these were some of the high level algorithms. And if you are interested in using it, there are also uh, it's easy to, I mean, there is also a Qiskit machine learning repository, but in addition there are also specific applications functions from let's say some of our startup partners who write application functions and then host it on our platform, so that anyone who wants to just directly use this application, let's say for the specific optimization problem, or let's say if you want to have the quantum machine learning classifier to solve binary classification problems, there are ready-made uh, applications that anyone can use and then run it. On top of it, maybe I missed adding a slide on it, but if you're interested in exploring different machine learning algorithms, there is also this Qiskit machine learning repository, which has implementation. It's completely open source. It has implementations of various machine learning algorithms. And if you want something new, or if you want to contribute you can also contribute to that. Okay. Any questions till now? So there is a question around why is industry focused on AI applications rather than AI computing systems? I think industry is focused on AI computing systems as well, right? There are different parts of industry that focus on this, but there has been a very significant investment in AI computing systems as well. I mean, let's say Nvidia and Google and IBM are like examples of industries focusing on AI, building AI computing systems. And I think it's more of the other non-computing industries that look at that, right? Okay, the next question is, why is integration of artificial intelligence and quantum computing essential, and how does it lead to emergence of quantum AI? Okay, why is integration of AI and quantum computing essential? I would say uh, at the end of the day, let's say if you are someone in the healthcare, life sciences, let's say research or an industry, you don't really care about okay which type of computer you use, right? At the end of the day, we want to make, let's say, advancements in drug discovery, right? We want to produce, let's say, new kind of medicines that are cheap and or can better solve a particular disease with lesser side effects and so on. What you care about is okay, how do we best leverage the best computing tools that we have today? And over the last decade, AI has grown up to be a very useful computing tool, and quantum computers are coming up to solve different kinds of problem statements more efficiently, uh, much more efficient, right? So it's important to understand the advantages and the limits of each of the computing tool, and then use them together so that we can better solve the domain-specific problem statements that we try to solve. So I think that's one of the primary reasons why integration of the powerful techniques that we have today, AI and quantum computing, are essential. Okay, so there's this question of, can I use QBraid for free? I haven't followed up with QBraid. You can check online. I don't know at this point what's the latest that we have. According which tool or website is useful to learn the basics of quantum computing? There are many things available, but since we uh, at IBM we spend, there is a lot of advanced researchers spending a lot of time in coming up with very useful learning material. I would suggest you to the IBM Quantum Learning platform, learning dot provide the link to that that talks about that covers everything from basic foundations to most the state of art research in the most advanced techniques. Okay, so you have tutorials from most basics to most advanced. So I think I will encourage you to go into that. And there are also some things I will cover in the later part of my talk. I think I was preparing for a 1.5 hour talk, so I think there is more content. I might even run over a bit. Let's see, but maybe I'll quickly go through that towards the end of the talk. Okay, so environmentally friendly. So surprisingly, what we have realized is quantum computers use much less energy compared to GPUs. I think there is a slide I'm missing on that. But I think when quantum computers become web-prescript, I think energy will be, relatively speaking, much used compared to the modern GPUs. We'll see how it evolves in the next few years. Okay, maybe I'll just go over some of the rest of the slides and then come back to the questions. So till now I talked about how quantum computers can be used to improve or to design new machine learning architectures. And now I will talk about, okay, the other direction, how we have been leveraging the modern advancements in AI to accelerate the adoption and the development of quantum computing. Okay, if you talk, I talked about like sort of multiple steps of running a particular quantum algorithm. First step is you sort of map the problem statement into quantum computer to encode the data in a quantum computer, and then you actually run the particular problem on the quantum device and then post process using classical. So in terms of both pre-processing and post-processing, we can significantly leverage the modern AI techniques to sort of accelerate what we are trying to do, in addition to sort of running quantum machine learning algorithms. So these are sort of four main pillars of work happening inside IBM about where AI has been used to uh, improve the adoption and the development of quantum computing. The first is designing code assistance for quantum computers. So, maybe I'll quickly go into each of these slides later. The first is designing code assistance for quantum. Second is optimizing the quantum circuits to be run on quantum hardware using AI. And the third is performing better resource management using AI. And the fourth is improving the results quality, let's say either in the diagonalization algorithm that I talked about, either to improve the quality of samples there, or to have better mitigation of noise, or to have better calibration of our quantum processors, or even like in coming up with discovering algorithms where quantum can outperform classical, right? Like there is new discovery of algorithms that to understand, okay, what are the other new kind of problem statements for which quantum can outperform AI, right? So even there, we leverage AI itself. Okay, so these are the four high class problems. The first is code assistant. Of course, like we have in any other domain, we want to make quantum computing easy, development of quantum computing easy and accessible to anyone. So there has been a very significant effort in developing code assistance for Qiskit, which is our tool for programming on quantum computers. So this sort of has 4 steps: developing sort of data sets to train a model, train our code assistant, developing the model in itself, creating a service that makes it easy for each of you to run this particular model, and then extensions in the modern like programming tools that we have either in Visual Studio Code or sort of these days it's very popular to run Jupyter notebooks for machine learning problem statements. So how do we leverage that in your particular programming workflow or in this MCPs where you can connect these code assistant to other kinds of uh, models that like LLMs that we have to like, let's say you already have a workflow where you have different models and agents connected to improve your workflow. So how can we connect this the quantum code assistant also to that is also work something that we had been doing. Okay, maybe I'll just skip this for the lack of time. The second thing, oh, of course, okay, all these models and the agents that we built are like open source, so I strongly encourage you to try using some of this. Okay, and also leverage it for your like Jupyter code extension. It's actually like very easy to install and then use. And there is also an sort of an automated quantum programming tool based on UI interface where we can plug in different modules. Let's say if you want to run this particular diagonalization, sampling based diagonalization algorithm that I talked about. Okay, it talks about first, okay, like which Hamiltonian to choose, which circuit library, which compilation technique to use, and then okay, different error mitigation and like the other execution modes to use, and what is the post processing that we want to use. So let's say if there is a UI where we can plug in all this, and then we have an AI based agent to automatically write the quantum code, Qiskit code for doing the same, and you can adjust the different parameters and so on. And if you want to optimize some specific tools, or let's say if there's a specific quantum operator that we want to use, you can specify in there. And we have leveraged AI based agents to sort of have this automated tool to make it easy. And there are also different demos for this. This is also open source and ready for you to use. The second place where we use leverage AI is in optimizing the computation that we run, optimizing the circuits that we run. So we use reinforcement learning to, okay, so or first of what is a problem statement that we try to use? You write like as a user, we write like high level programs, right? High level, let's say Qiskit programs. And we have to build a compiler to break down the high level programs to the most efficient set of instructions that the hardware can understand, the machine understandable instructions, the pulses, the that we send to the hardware. And there are different steps involved in that, and there are some of the more computationally expensive steps, and there we have used reinforcement learning based algorithms to perform this in a more generic and an efficient manner. Okay, to convert high level problem statements to low level instructions efficiently. So you can sort of read some of these papers on how that performs. And similarly, okay, like I talked about, like let's say if you submit a quantum job, we want to understand how long it will take to perform that, right? So, and that is actually used for us in many different scenarios. So we have used AI to sort of understand. It's one of the methods that we use to understand how much time the particular quantum job can take. Right? And similarly, there are also some of the other advanced quantum tools that are exist, like circuit cutting and so on. We have used AI to understand, okay, like whether it's effective to use some of these quantum tools or how effective it will be used to some of these quantum tools and so. And finally, the fourth sort of pillar where we use AI for improving the quantum development and usage adoption is in better mitigating or improving the results, quality of results. So that ranges from using AI to improve our calibration of our hardware to at a higher level using AI to uh, identify better decoders for our error correcting codes, or coming up with better heuristics using AI to better improve the noise model of our hardware and mitigate the noise of our the the quantum computations we run. I think as you go through the course, as you learn further more about quantum computing, you will like even more appreciate how some of these AI techniques had been used to improve some of these steps. And then finally, we also use AI to identify the hard problems to solve. Okay, uh, there is this never-ending pursuit of finding new and newer problem statements where quantum will outperform classical computing and provide advantage, right? There has been many candidate problem statements, and there is an exploration for finding newer and newer problem statements. So one of our research teams also use AI to find new hard problem statements. I mean, new problem statements which are very hard for classical computers and are easy for quantum computers. And expanding that, there is also sort of an algorithm discovery. How can we use the modern AI tools to come up with new classes of algorithms? Because AI has been producing new results, interesting results for coming up with new classical algorithms. So we have been trying to extend that to see how the modern large language models and extensions can be used to come up with either new quantum algorithms or new types of using the existing quantum algorithms. Okay, so yeah, I mean, this is just a nice picture that the Quantum Plus AI team has developed to express the synergy between this, where quantum can be used to improve AI, and we have also used AI to improve the quantum development and adoption workflows. Okay, so the last part of my talk, I want to highlight the different learning resources available and how you can leverage all this to include in your curriculum and to teach it and uh, to significantly sort of improve the learning experience for your students uh, in quantum computing and sort of partially AI. So yeah, I mean, like there are three different components to it, right? For building a quantum workforce. First is actually developing the hardware software tools. The core is education, and then in connecting these tools and building a powerful community. So one of the things we have is the Qiskit classroom modules, where uh, we have different modules around like Jupyter notebooks, which explain some of the key concepts, uh, for different of the existing courses that you already have. Let's say there are some physics courses that you have and where you want to explain some of the quantum principles. There are some existing modules where you can just plug in and explain some of the basic principles using the hands-on Qiskit code. And for different of the popular courses that you teach across the different departments, there are modules available that you can easily plug in and use it for demonstrating some of the things that we want to do. And the link that I posted, the next one is an extremely exhaustive set of resources for you to learn in quantum computing. This is just one snapshot of it, but this already tells you, the range of things available from the most basics to the most advanced things available. Okay. So for any topic that you want to learn, there has been an integrated theory and hands-on components into like how that can be leveraged to sort of do to teach these concepts. Okay, I mean either to learn for yourself or to leverage them for teaching your students. And like one of the thing that we always try to do is for any, I mean it's a rapidly advancing field, right? And whenever a new technique that comes up that we think is reusable, we create a tutorial of that. I mean the name sounds simplistic, but if you look at the tutorial section, those are demonstrations of the most advanced research result that came up just a few months ago, that our some of our top researchers, we have spent time trying to understand the sort of the most fundamental aspects of it and most sort of reusable aspects of that particular research, and then try to convert it into a form that any student and learner can run it to understand the most foundational thing that has come up in just a few months ago. So there has been a lot of emphasis placed on and a lot of effort placed on developing this learning platform to convert even the most advanced and new techniques to in a easily consumable form for students and learners. So I strongly encourage you to go through the learning platform and oops, and like yeah, go ahead with this. And one of the things I want to emphasize is that as you go through the learning platform and the courses, you will also realize that there is open source software and code available for everything that you learn, starting from the basics to the most advanced techniques. And something like over the last few years, the theoretical and the conceptual knowledge of quantum computing has been steadily increasing. But what we find among the students and in the broader ecosystem is that the ability to program and demonstrate the concept learned uh, has been significantly lagging behind, even though we had been improving on the conceptual understanding. So something and that's actually like critical, like being able to demonstrate and learn is critical for both advancing the further research, and it's necessary for anyone to get a job in industry, in the quantum computing industry or any of the industries that leverage quantum computers. So something I strongly encourage you to sort of do when you're learning, and to also certainly encourage the young students watching this, is to go through a hands-on exercise for any theoretical concept that you try to learn, especially because everything is open source, right? So specifically, one workflow I strongly encourage, right? I'll sort of, this is a final example that I will give, and this is something you can try to do for any library of interest or anything that you're trying to learn. But let's say you're trying to learn about compilers for quantum computing, right? Uh, Qiskit is a particular Qiskit is a library that helps you write programs in quantum computers, and this specific SDK also converts the high-level programs into very efficient machine understandable instructions. Let's say if you want to understand about this, I like you first try to think about, okay, what are all the uh, basics that are required to do it, right? So of course some of the quantum information basics are required, and traditional software things are required. In addition to that, it will be useful to develop skills around some of these sort of low level programming aspects, and the sort of, since this particular library is written in Rust and Python, so you also learn that, and then the traditional data structures and algorithms required to do that. So essentially, whenever you pick a when you try to learn theory, you look at the corresponding open source software module, you break it down into the different basic tools that you require. Anyway, you will probably have seen some of this in your initial years of your curriculum. You have taught some of this in the initial years of curriculum. If not, okay, these things you have it in the initial years, so that when you go to the third and later years, for someone trying to use this, they have all these foundations covered. And now, when you try to use a particular repository, I suggest, okay, you start the repository if that's of interest to you. And these are some of the things. If you don't already know, I suggest you to sort of search for these and learn this. Just understand, okay, how to fork a particular repository, and look at what are all the open things that are available. I mean, like if you go to Qiskit repository, there are about 930 open issues, which means that these are all the new features that have to be added to that particular repository that we know. And you learn the relevant background and you write code corresponding to it, and you can raise so-called you can contribute to it by raising a pull request. Okay. And this is actually a practice I suggest all the learners, especially students, when you are in your initial years, or for faculty, I want to encourage your students to do it, to strongly couple teaching the theory and then making them understand how to demonstrate that using code, because that's one of the things that we think it has to be strongly developed in India, and that other countries are much better off in doing it. So as you teach newer and newer concepts, I strongly encourage you to learn through contribute. And anyway, like I mentioned, starting from the foundational modules to advanced application modules, there has been sort of the code is available in open source, so it makes it very easy for you to do this particular practice in whatever you teach, or at least like encourage, certainly tell the students to do this. And let's say sometimes they also, out of their own curiosity on the side, they do all these aspects. Okay, that is sort of the summary that I want to end my talk today with.
Thank you very much. I now request you can take 2 or 3 questions, sir. Anybody can raise your hand so that you can ask the question.
Dr. Dinakar.
Yes, sir.
Yes, please.
I'm Dr. Illa Ravi, Principal, Dr. LHR Government Degree College, Mailavaram, which is a rural college. I'm the only layman in the group which has joined the this webinar. Sir, I have a very candid question.
Okay.
I got around 70 students, preparing them for Qiskit. I made them undergo a certificate course in Python with AI and then Python with Python full stack. And I also started a quantum innovation center in our college, and we have been eagerly waiting for 19th, the Qiskit program that is going to happen from 19th onwards. That's all really wonderful. And though we might be a little ambitious as a rural college, but we are still striving hard to get to it. Now, my question is that do our students stand a chance for employability placement?
Sir, I think we'll take it step by step, right? So I think I will suggest you to go through that NPTEL course, okay? And there will be different programs where we'll do, because that has been an ask from CM Garu as well, right? On how do we start with the basic courses and grow towards some of the advanced courses, and what are the pathways of employment, internships and employment that come up. So I think that is something, as we right now we are in step 1, and very quickly we'll go towards the advanced steps that we want to do. And I think Anil sir and the team will keep everyone up to date with all these activities that come in, right? But there is
And
pathway here, and you
Yes, sir.
don't have to be worried. So actually, we are lucky to live in a world where we don't have to be worried about whether we're in a rural college or in a very urban advanced college, because the gap has been reduced significantly. I'm not saying that there is no gap, but we can probably appreciate 10 years ago versus now, the gap is like extremely reduced. So students do not have to have this mental block about, okay, from the rural college or not, because thanks to like the different internet based tools that we have, the exposure is almost similar. We just have to make them not think about that they are from a rural college and doing it. In fact, uh, one of the one of our recent hires who will join next month in our team is from rural and hilly parts of Andhra, uh, in a very remote regions. And we were happy to see that someone who has grown up in the rural region has can do some of the most advanced things, can develop himself to most advanced things. And even though we try to only look at the quality, right? Overall, that this is a team. He will be part of the core development team in Qiskit, and that's one of the most advanced teams that we have in IBM Quantum in India. And it was happy to see that someone who grew up in rural regions in Andhra and I mean in India overall, right? Some rural remote community that can keep up with the state of art and develop himself to be that. So I think this world certainly allows you to.
Yeah, thank you for the reinforcement. And I have one more point to add. I mean, I have a slight understanding of, the kind of the race for quantum supremacy that is going on, and the way GPUs and QPUs are being amalgamated. I mean, like, being brought together. And I've been reading a lot on that. But, what surprised me is that, all the time quantum computation is people are talking about it as being used for in sciences, chemistry, new molecules and new pharmaceutical tools and all that. But I believe that quantum computation would be having a wonderful role to play in social sciences, where we have numerous social variables, and combined with the unpredictability of individuals and groups that act. So I think quantum computation has with real potential and real power in social sciences, more than in physical sciences. Maybe we can come out with a new synthetic element with more than 118 atomic number, but that won't matter much. But I mean, real things that have to change is for example, the social media. I mean, if you can apply quantum computation to social media and find out which are the fake ones, and how to navigate in social media, I mean, those things will be more wonderful. Maybe that area is a gray area where quantum computation, I mean, the people professionals in quantum computation have to think.
Yeah, I would say, I mean, like I talked about two high level classes of problems, right? One was, of course, the chemistry nature simulation problems. The second class, when I talked about the data processing problems about around optimization and machine learning, I certainly agree this kind of anomaly detection and other things are also something that we think is promising for us to explore using quantum computing. Yeah.
Yeah. Thank you, sir.
Dr. Ravi, really appreciate your enthusiasm being a government college principal. And I think it has happened to be you are in Washington. Why can't you visit the Weiser there? That is very much there. That is Washington Institute for STEM Research. You can go there and visit, and you can interact that your own students are doing Weiser program also, so that you may have a very good exposure.
Sure, sir. I would like to go. I mean,
Yeah,
am I permitted to? Like, you know.
yeah, you can take. You can tell them that you're from Andhra Pradesh and where Quantum Mile is coming, and your students are also enrolled for this Wiser program.
You help me through. I would love to
Yes.
go there.
Sure,
Thank
sure.
you. Thank you, Dr. Anil.
Yeah. Any other participants, please? You can one or two questions only. You can raise hand. Any other faculty members? Yeah, Sheikh Karimunisa, madam, please you can unmute yourself.
Maybe the question, I think ma'am also had the question on chat. Maybe that's what she's trying to ask. Maybe while she's unmuting, I'll first answer that. The question of, does quantum computers replace normal computers? The answer is no. It will be one other type of computer, but an extremely powerful type of computer for specific tasks. We expect, like there'll be certainly like classical and quantum computers co-located and doing their own, whatever their own good at, right? We're not expecting one to replace the other. We'll leverage the advantages of both of these because they are different.
Sir, one more question I have put in the chat box, that is regarding the energy use and the water usage for the AI.
Right. I think I don't have a generic answer to that. There are problem statements where when we analyzed AI, quantum uses less energy than AI, but I think it's probably problem specific, and also there is it does use a lot of energy, but I mean what we have seen till now is AI does use a lot of energy, but it has given enough more promise. So there is a trade-off between that is something that's all for us to explore.
Sir, always we are talking about the positive sides of these technologies. So other side of the AI is a lot of scams are going on using this AI technologies, sir. What about that, sir?
Yeah, it's something unfortunately that
For
whenever a
example,
new powerful tool comes up, there is a good way of using it and also a bad way of using it. And I think there is a lot of effort from technologists, researchers, and government to mitigate all the negative uses of the technology. Yeah, but sometimes it's also about moral aspects that, like, if we have something powerful, it's on us to use it the way that we want, right? So as teachers, we will also actively also encourage, I mean, like, strongly teach everyone to do the use things in a good way, right? But technologically also there has been strong efforts put in to mitigate the negative uses of AI.
so one more thing, sir. These quantum computers have come in use for normal people, sir. Common use.
Okay, I mean it's commonly available. You can access quantum computers through cloud. If you just go to quantum.cloud.ibm.com, so we have this 10 minutes of free access per month and a list of very interesting things that we can use using that. It has been there, in fact, for the last 10 years. Quantum computers can be accessed through cloud and that you can use to learn and perform certain experiments.
But it's not for general use, no? It's only for some medical purposes, some other.
Oh, that way. Okay. Yes, applications are different. Like there are mostly for specialized applications. And if I guess when you talk about general use, you mean the day-to-day activities, let's say I mean, there are many of the day-to-day activities. If you think the current computers are good enough, then yes, there is no use for a quantum computers. It's interesting to explore quantum computers only when you reach the limits of what you can do with the best computers that we have today. And then if you want to see something more advanced, then that's actually when it gets interesting to explore the use of quantum computing.
Okay, thank you, sir. Thanks.
Any other faculty members? Can raise hand. Okay, if there is no questions, there are no questions, we can close this session. On behalf of AP State Council of Higher Education, I thank you very much, sir, for your wonderful presentation. And it's really great help for all our faculty as well as students. Definitely, sir, most of our students now, actually we have started with 1000 faculty members. Now in QT06, there are around 600 faculty still they are learning. Apart from this, almost by last week, around 35,000 students across AP, they have registered as this NPTEL program. And once again, I request all the faculty members to encourage your students to register. I think another question is there. Madam, you can unmute yourself. Hello.
Yeah, I have unmuted, sir.
No, not your madam. No.
Okay.
Another faculty, Nagajyoti, madam, please. Yes, madam, Nagajyoti, madam, please. You are now unmuted. Hello.
Hello, sir.
Yeah, please. You can speak.
How this will be helpful for the VLSI and other branches correlation, sir?
So let's say for VLSI semiconductors type branches, there is a similar interfacing like we are thinking about AI and quantum. What I mean is, for designing better quantum chips and quantum computers, we are leveraging a lot of tools that VLSI and semiconductor communities, industries had developed. Okay. So anyway, these are also one type of quantum chips, right? Processors. So designing and development of quantum process is something we leverage or we build on top of the tools that are developed by design automation experts or like the VLSI and semiconductor communities. Okay, that's this direction. And then once we have, like when we have more and more powerful computers, if you look at the core problems that the VLSI or semiconductor industries or like let's say tools that try to develop is some kind of an optimization tool. Like, okay, VLSI, you look at, I don't know, like how do we design the chip so that it consumes less energy, or how do we pack more processors into that? Like, if you look at some of the core problem statements that the VLSI and semiconductor industries do, then there has been potential for leveraging some of these quantum algorithms to come up with better VLSI tools and algorithms themselves. So there is potential that direction also. So
Thank
it's
you,
a both way synergy, very similar to how I explained where quantum development can leverage AI and quantum large quantum computers can also come up with new AI architecture. So that way, both VLSI community also there is a mutual benefits from working with quantum computing.
Yes, please, Velanki Chandrasekhar ji, please. You are now allowed. Please, you can interact.
Namaste, sir. Good afternoon.
Good
Am I
afternoon.
audible, sir?
Yeah,
Yes,
yeah,
sir.
then
Please go ahead.
Very good afternoon, sir. Thank you, Professor Vinayakan Dinagaran. Really a nice presentation. And first of all, congratulations and heartfelt gratitude to the APSCG for conducting this webinar series on quantum computing. We are able to update ourselves. And it is very nice, sir. And also, one more request, sir. Please provide us participation certificate so that it is a boost up thing for all of us, sir.
Sir, that is not an issue to be asked to the resource person. We are APSCG is providing after 20 sessions, 20 webinar sessions. If you attend, we will provide, sir. Every
Okay,
day,
sir.
every week, I am telling that.
Okay, sir.
If any doubts on this quantum or AI, you can ask the questions.
Okay, sir. Thank you very much, sir.
Sure.
So if there are no questions, we can end up the session. I once again thank you very much, sir, for accepting our invitation and sparing your valuable time to address all our faculty members. And not only that, our students are also watching YouTube live. That is also streaming. And once again, I thank you on behalf of AP State Council of Higher Education.
Cool, sir. I also really heartfelt thank APSCI and the AP government for all the initiatives that they are doing. And as I said at the beginning, I'm really, really looking forward few years from now to see the fruits of all the efforts that we are putting in together. So,
Yes, sir, thank you.
thank you.
Now I can end up this. I can close this session.